Hey y'all, it's Mr. Boyd and your personal math teacher. I'm back again, and today we're going to talk about how to use studies wisely. This is such an important thing to think about, and it's really just critical thinking skills around what we've already learned about study design. Because if you don't use your studies wisely and if you don't have really good background methodology, you can come up with some really bad conclusions, even if you're well intentioned, and even worse if you're not well intentioned. You can come up with some really crazy results and be very misleading, which could be really harmful to us in society or to a population of frogs in a pond or whatever it is that you're researching. Okay, so that's what we're going to look at today. We have a couple key ideas. The first one we're going to talk about is sampling variability, and that's something that can happen that you have limited control over. Okay, there's something we're going to learn what we can do about it, but we can't control it. Okay, and it's the idea that if you are going to take measurements and you're going to do a sample, the measurements you get in the sample may not match the reality of the population. So let me give you an example here. So a class of 32 of my students had the following percentages on a test. So guys, these numbers on the left, the 1 through 16, that's just saying like student number 1, student number 2. I took their names off because that would be really unethical. And so this here, that's just numbers of the students. Okay, so in black, I'm kind of bracketing the student number 26 or whatever. Okay, and then the numbers that are here, I'll highlight them in blue. So these are the actual scores, okay, percentages. Okay, so if we use a sample size of 5, and I'm not going to actually do the sampling right now, but if we use, in class we do the actual sample, but for the video I'm not going to. If we take a random sample of 5, there's a lot of different samples we could get. Okay, and so we might get numbers like this one and that one and this one and that one and that one. You go, okay, cool. Maybe that's representative, maybe it's not, but you end up with a mean. Okay, so you get the mean or the average test score. And in this example, there's 32 students. So yeah, I could calculate all of them. But in an example where for like if you're gonna take the blood pressure, you want to know what is an average blood pressure in our country. You could take the blood pressure of 1,000 people. There's not a way to do it for everybody. You can't do a census, and so you're not gonna know the actual mean, but you're gonna have a prediction. Well, what could happen? What could possibly go wrong is kind of what we need to understand. Like, what's the worst case scenario here? So in the example we just did, what's the worst case scenario? What's the lowest possible and highest possible average? So the lowest would be the average of these 1, 2, 3, 4, 5 numbers. Okay, the lowest, and that would come out to be an average of 0.6%. Okay, and I'm doing that one in my head. That one, I think I did it right. We'll see. And then the highest, it is possible that with genuine, or the highest, that with random sampling, you could end up taking these 5 highest. And so if you did that, I'm going to need to use my calculator to add that up. And so the highest possible you could read is 97.2. You could have a sample size, or excuse me, a sample mean as high as 97.2%, which clearly is not true. I mean, just glancing at the data, you can see the average test score is not 97%. So you see how even with randomization, you could still get really wonky results. So how can we fix that problem? Or what's going on here that's allowing that to happen? And the question is, how can we mitigate that problem? Well, the easiest way to do it is to have a bigger sample size. What if instead my sample size was, so this is a sample size of, or we'll write it like this normally, n, not m, n equals 5. What if we had n equals 32? And that's obviously the biggest sample size we could have. That's a census. Well, that would give us the true, I mean, these numbers would be the same. Whatever you get here, whatever, and I don't know what they are because I didn't calculate them, but you get the same number for both those because there's only one way to take a sample of 32 people. Okay, and if you had a sample size of 10, this 0.6% and the 97.2%, they would get closer to each other. Okay, so the easiest way to deal with sampling variability, yes, you want to have good sample methods, but get a bigger sample size. And that sounds really easy, guys, but a lot of times it's hard to get a big sample size because it costs money and it costs time, and time often is money if you're hiring somebody to do a study, or if it's your time and you're going to have to spend a whole bunch of your life. So that's a hard thing to do. That's one of the things that in research we often grapple with is how do we get a sample size big enough to where we can feel confident in our result? Because if our sample is small, like 5, it's really hard to have any degree of confidence. Okay, so sampling, we're going to learn much more about that in a later unit. We're going to actually quantify it with equations and see specifically exactly how sample sizes affect it. But that is something to be aware of now as well. Okay, let's look at another example of sampling variability. All right, we're all huge Justin Bieber fans and are very happy because his tweets are blowing up. After recording the number of retweets he had on 30 different posts, we find that he averaged 3.1 million retweets per post. Wow, nice. So do we think that 3.1 million is the true average for all of his tweets? And he has a lot of tweets. If you went and looked at every tweet he's ever had and recorded the number of retweets, do we think that 3.1 is the exact number we would land on? And guys, your answer to that should be a resounding heck no. Okay, and it could be higher, it could be lower, but the odds of us taking a random sample and nailing it on the head, getting the exact right number, is basically nil. Okay, I mean, it could happen, but it's pretty unlikely. Okay, and then the second question, I want you to, hopefully you can answer that one. What would give us a better picture, and I don't mean literally a photograph, I mean like a better idea of what the truth is? Would a random sample of 30 posts or a random sample of 100 posts be better? Okay, when it comes to sample size, more is better. Okay, I'm going to say if you can afford it, more is always better. And in this case, we could probably afford the time to look at a few additional posts. Okay, so more is definitely better. Looking at all of his posts would be the best, but that could take way too long. All right. Next thing we're going to talk about is the idea of statistical significance. If you listen, anytime they're talking about research, it's like, oh yeah, the patients showed a significant reduction in their A1C levels, okay, for maybe a diabetes treatment or something like that. So let's talk about what that means. Basically, and this is the basic idea, we're going to quantify this in a later unit, but the basic idea of this is, if the results or whatever happened is too unusual or too strange to be most easily explained away by random chance. Okay, so let's look at two like real world type examples of that to get that idea. So here's the first one. In a cancer trial, 58% of the patients in the new treatment group, that's the new treatment, that's a newly developed drug of some kind, 58% of those folks are in remission after 5 years. And 55% of patients in the conventional treatment group are in remission after 5 years. Is this likely to be statistically significant? What that's really asking is, in this trial, you have a 58% survival rate versus a 55% survival rate. Is that difference big enough? Is another way of asking the question. Is that difference big enough to be very convincing that the new drug works better than the old drug? If you are an oncologist and you're going to be prescribing to your patients, are you feeling like, oh yeah, I definitely need to use the new drug, not the old one? Do you have that feeling? And at this point, we are not quantifying it, so that's just a gut feeling you would have. And the answer most people would say is probably not. It doesn't mean that it's not as good, but we don't have the data to say like, yeah, oh, it's definitely way better. Let's look at a different example, and maybe this will help. Example 2. In our study of online learning versus classroom learning, it was found that the average score on the final for online test takers is 68%, while the average for classroom learners is 82%. Is this likely to be statistically significant? Let me ask that question another way. Is this difference big enough that it makes you believe that classroom learning is better than online learning based on these numbers? Probably, especially when you think about it like this. 68% is a D, 82% is a B. Guys, we've all been in school long enough to know that a B grade and a D grade are very, very different grades. Okay, that's a big difference. You go, well, that's 14%. It's a D and a B. That's a big difference. Okay, so that's a yes. That's probably going to be statistically significant because that's such a big improvement in the grades. You go like, whoa, that makes me think that it's very likely that in fact classroom learning is better. Okay, now one thing that throws people off is I've had a lot of students say like, wait, but Mr. Boyden, in the first example, 58 is bigger than 55. So how can you say that? Of course it's a difference because 58 is bigger than 55. Right. But guys, understand that if you took two groups, group 1 and group 2, it's very easily possible, and let's say they had the same treatment. Okay, they both had the old treatment, and one of the groups had a 55% survival rate. Would it be weird to you if the other group had a 58% survival rate? That could easily happen. You could just have a few patients who happen to live that long. Maybe their cancer, for whatever reason, they respond better to the treatment. These are like little differences. Okay, so you'd say, well, yeah, I mean, that could happen. I mean, with the same treatment, it's not like 55 is a hard, fast number. It's this one particular measurement came out with 55%, and this one came out with 58. Now, if this number was like 78, or even 68, even at 68, That would be a big difference. Think about it like this. Imagine you're one of the cancer patients and you have a choice. Let's say you knew these data, you had a choice. And it's 55% versus 58%. I mean, yeah, you probably would choose. You're like, 58's a bigger number. Sure, I'll take that one. But if the doctor said, oh, actually, the 58% one, we're out of that one. You're going to have to wait a week and it costs 5 times as much anyway. But you might be like, okay, fine, 55% is close enough. But if it's 68%, you're going to be like, whoa, 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 whoa. No, 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 no. We're not doing 55% when I could have 68%. That's a big difference. I want the 68%. Okay, that's a way you could kind of in your own mind think about statistical significance for no. Okay. Inference is something we're going to be doing later. We're going to be just using the results of a study to draw a conclusion, and that's the exactly what I was doing here with statistical significance. If you have a statistically significant result, then you can make an inference. An inference here would be like we would say for this example, we would say classroom learning is more effective than online learning. That's an inference. We don't know for sure, but we have data that's convincing. Okay, we're convinced of it because the data are strong enough. And that's really what statistics is. Okay, it's taking data that is incomplete, doesn't include everybody, and saying based on this, there's reasons to believe that this is a real difference between classroom learning and online test taking, for example. Okay. Last thing we're going to talk about, guys, with studies, and we've talked about it a lot already, but you always have to consider ethics as you're designing and you're doing a study. So in the real world, here are things that happen. If you're going to do a study, the first thing that has to happen is it has to be approved by an institutional review board. This is a panel of people who you write up your research proposal and you explain, here's what I'm going to do exactly. This is exactly what I'm going to do. And then they look at it and they can ask you a question and say, well, wait, we're not really sure about this. Or maybe if you change that, or are you going to inform the people of this? Are they going to be signing off? Do they have choice? Things like that. Okay. The second thing is your subjects, and this is particular to human subjects. If your subjects are human, they have to give informed consent. Okay. Now, let's talk about this word informed. Consent just means they agree to it. But back in the day, doctor comes in, they're like, all right, let's do this, sign it, yada, 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 and you sign, and technically you've consented. We realize that that's probably actually not ethical. Your provider or whatever, if you're doing a medical or drug trial, they need to explain to you what the risks are and what the side effects are. They have to explain to you that it's possible that you're going to have a placebo. It's not a guarantee that you're going to have this new treatment, whatever it is, or you're whatever. You have to understand all the range of possibilities. If there are known side effects, they have to tell you. Okay, they can't say, "Well, you agreed." Nope, that's not ethical. Okay, and so you have to do that. The third thing is individual data has to remain confidential, and this is especially with medical stuff. If you were doing, sometimes you're in biology, you do a study with salamanders in a lab. Well, okay, you're not really violating a salamander's privacy by saying, oh yeah, this one salamander, it grew its leg back or whatever, which is a real trial. They do stuff like that. But this is generally with humans, you have to be additionally cautious. Okay, their data must remain confidential. If you have a woman named Sally who has this miraculous recovery, you can't go tell her, oh guys, Sally, blah, blah. You can't do that. It's nobody's business that Sally had a recovery. She's just a human being who's trying to live life, and you do not give up your right to privacy when you participate in a study. Okay, not to like public privacy, where like it be published that you did this or did that. Okay, and then the last thing I want to review today, and we've talked about it, but I want to give you a chance to have it in your mind again, is what conditions you have to meet in order to establish causation. So, do you remember what conditions you have to have causation? Okay, you need to have a randomized, controlled experiment. You need to have those 3 things, okay? If it's not randomized, forget it. In fact, even with sampling, if it's not randomized, forget it. Nobody cares. If there's not a control in your experiment, it's not a very convincing result because you need to establish that baseline. And it has to be an experiment because you have to manipulate one variable and demonstrate that that causes a change in the response variable. Peeps, thanks for watching. That's it for today. It's kind of a little bit of a shorter one today, which that's all right. I hope you enjoyed it, and I'll see you next time.